Okay, hi everyone. So for today, I would like to discuss about the next chapter, chapter number 3, intensity transformation and spatial filtering for our subject, digital image processing. Okay, so the content for this video will be covering the spatial domain processing regards to the spatial and transform domain processing. And we will talk about the intensity transformation afterwards. So this one, I think the majority of the chapter number 1 is about this one. So basically intensity transformation discussing on the 1 pixel perspective, while the second part of this chapter will be talking about the spatial filtering, whereby majority of the discussion will be covering the neighborhood situation, condition, and environment of each pixel towards the image processing technique. Okay, and not to forget all the classical technique for intensity and the spatial filtering will be discussed. I think both part, so part 1 and part 2, so will be covered. So for this video will be part number 1, intensity transformation. At the end we'll be talking about the example and application whereby where does the technique will be used and so on and so forth. So let's get started. Okay, a little bit background about the intensity. So all the images so far, the technique has been discussed, was discussed in this particular chapter, are implemented in spatial domain. Okay, so we have been discussing lots or many parts of the coverage for image processing in chapter number 2, whereby we use the plan containing the pixel, so indicating an image, right? So the plane. So the plane is whereby consisting of x and y. X and y. So this is basically happen in the chips, CCD chips. So whereby observed by the camera happen. So this why after the sampling and quantization happen, we have in JPEG or PNG and bitmap, right? Okay, so this is what we have done so far, is basically for the spatial domain. Okay, whereby it's operate directly on the pixel of an image. So all the pixel, as opposed, for example, the compared to the frequency domain, whereby here. So this one will be covered in the next chapter, chapter number 4. Hopefully, there will be the next chapter to be covered, whereby we will talk about the Fourier transform a bit, and later on how to transform the image to another domain and return back the domain in the image profile. So that will be discussion on the next chapter. All right, so the best again, I think this will be covered last chapter. So the f, x, and y happen to be an image as the input, while the g is also an image considering as output. Okay, so while this one is operator, so whereby it depends on how we do the operation on that particular images. So for example, we do additions, summation, and so on and so forth, right? So whereby the x and y is dedicatedly located at the point. So in example x and y, we have the example 3 and 2, location for 3 and 2, right? So here, so that would be x and y in terms of the pixel or location of the image, right? So in example, there will be a figure down below. So this is 3 times 3 neighborhood. Okay, so right now is x centered by x0 and xy0. This one is the transformation of neighborhood picture. Okay, so whereby we can say that neighborhood processing technique here. So we have 1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry, not this one is 8 neighborhood pixel for this particular center. Okay, the neighborhood is moved from pixel to pixel in the image to generate an output images. So basically the images will be moving from the left top corner to the how to say, let's say we started from here, so they will be going like this and goes like this and goes like this, so until the end of the all the available pixel in that particular image given f x y, right? Okay, so now we have just now we have g x and y, so this one is f x and y, right? So from this chapter, basically we will like to use S and R as the output and as the input images of or group of pixel. Okay, so the smallest possible neighborhood. For this case, for the second example, the one that we have just now is 3 times 3 pixel neighborhood, while this one is 1 times 1 neighborhood. Okay, so in that particular image, basically the idea of manipulating or the pixel is whereby happen in the single image to the others, right? So this particular pixel will be compared with the two intensity transformation function, whereby the first transformation function, so this is R, okay, is the kind of contrast stretching function, they call it, kind of smooth one, while this one is like floor function, okay, rectangular one. So this one is being called thresholding function as a T, guys. So contrast stretching function is also as a T. Okay, so both of them are the T, means operator of that particular purpose. So meanwhile, if we try to give the R is here, basically the moment that we give K is less, oh sorry, it's not K, let's say R. So the value will be 0, right? So when K larger than R larger than K or equal will be this particular intensity, right? So similar to goes to this one, from the dark to the light, so we can have a smooth one for describing the intensity of that particular image. Okay, right? So in overall, this intensity transformation and spatial filtering is basically for enhancing. Okay, so enhancing the image, whereby the enhancement is the process of manipulating an image so that the result is more suitable. So that would be keyword, then the original or a specific location. So whereby we have two things to be considered here. One is the most suitable picture rather than original, and the second one is for dedicated specific application, whereby okay, the specific here is important because it established the outset of enhancement technique and the problem oriented. So example, we did discuss about the NASA population images, remember? So the one that we have, the river junction and so on. So without enhancing the images, whereby we can't see the population near to the river, right? So this part. So after enhancement, then we can see the true population or houses that located from the satellite images. So that would be enhancements. Okay. So the intensity, the way that we try to convey to the students regards to the intensity transformation, we would like to segregate the idea of intensity transformation, whereby we have T over here just now. So this one is function. We have several 4 to 5 function transformation regards to the intensity. So the first of all is image negative, right? So image negative is the problem or situation whereby we can relates to the one that we have in the previous generation. We have Kodak, So the moment that we press the button of the camera, so the picture will be stored in the kind of film, right? And black one. So then we will bring along this Kodak after we put it in the case of around. So we send to the shop, and the shop will be printing out the 3R or 4R, etc. or 5R. So that will be the negative, right? So whereby the image negative over here is respecting to these issues. So whereby we can see, if any, 0 is black intensity, guys. To the largest, I mean L, is white. Okay. So no matter what L is all about, so it depends on the N bit. Let's say we have, okay, this is L and L bit. If we have L equal 3, so meaning the level that we have over here is 3 minus 1 is 2, right? So meaning the level for this 3-bit image, 0, 1, 2. So the idea of this set would be 2. So meaning to say we have 3 scheme. So this is the most black. This is the gray kind of. This is white. So that would be indicating the 3 bits intensity level. Okay. Take a look at this set when we talk about 8. 8 meaning 8 minus 1. So 0, 1. So means 0 to 7, right? So in this particular example, we do have 7 level of intensity at that particular application. So that would be L. Okay. So is obtained using negative transformation. Okay, normally the negative transformation, so S is taken from this one, if you can remember. So S is the function for output. Okay, L is depending on the largest bit for the chosen application, whereby if any we use 3 over here. So 3 minus 1 minus R, so means 2 minus R lah. Okay, so that would be the things. Okay, so the negative is basically reversing the intensity of a digital image in the manner produced the equivalent of photographic negative. So this would be the same as the one that we talked just now. Okay, so this would be the intensity, guys, while the negative would be this one. Okay, so not to forget, by looking up to the figure 3.3 over here, we have 1, 2, 3, 4, 5, 6, 7. We have 7 types of intensity graph. Okay, so we have negative, we have the identity, we have the log, we have en route, and so on. Okay, right. So we have, so far for the first technique function, we chose to discuss about the negative. So negative for the S is L minus 1 minus R. Okay. Okay, so this will be the example of image negative happen in the momogram images. So this will be the breast image by momogram. So the thing is happen in the original image momogram, whereby we can't see the impact of the breast tissues. Okay, so the things that indicated by the light pixel is the tissues. So tissues is the whereby it reflected to the cancer. If we have a kind of is kind of abnormal situation of tissues happen in any one breast. Okay, So when we talk about the negative, the moment that we change or enhancing this particular image from the mammogram image to negative image obtained by this particular equation, so basically we can see that the changes or abnormality of the tissues or cell in the breast happen here and particularly here, right? So that would be image negative transformation function, one of, okay? So the second one is the log transformation. Okay, happened to be discussed earlier in the previous two slides. So this will be the log, guys. Okay, here we can see that the log, what the log intensity transformation doing is to, okay, this area would be considering you see, this one is more or less for the black area. So while this one is the white area of intensity input, the images, right? So we want to describe more on this area rather than this. Okay, so we try to shrink the black area in because some application, this one is kind of more than enough or unnecessary to expose more data or information about that particular images, right? So that would be enlargement of higher level value for intensity. So that would be a certain application. So the application so far has been mentioned of the log is when we have a Fourier spectrum display by the grayscale. Okay, happen to be that both of the image have the same 8-bit image. Okay, but the thing is, take a look at the left hand side. The grayscale happen to not to expose the lighter one. Okay, because of this is a huge or big pixel density of width and height. Okay, so when we talk about the Fourier transform, because this one happened from this large of scale, guys. Okay, so whereby the truly black and the very dark black is looks like similar, whereby it is happening in the middle. Okay, here and there. So if we change this to log intensity transformation, so we can see clearly this one. So whereby from a bigger kind of intensity color, so to the like 6, okay, color to be exposed. Okay, so to see as a result in the same display. So whereby here we can see that this region is not happen for the previous display images, this area to this area, and that. So that would be a log transformation. Okay, power law gamma transformation. So the power law have the equation as S. S is likewise we have this particular things. Okay, so R is the input, so this one is a gamma, so C is the intensity. Okay, whereby okay, C and gamma are positive constants. So the equation whereby sometimes is written like this. Okay, sorry. So this is happen to be as gamma, guys. To account of offset. So however, offset typically have issue of display the calibration. Okay, that would be okay. So in this particular area, power law gamma transformation. So the gamma has very own task to provide a curve. So you can see over here the curve is like this. It's very sharp curve and reducing up to here when we push up the value of gamma. Okay, so the moment that we wanted to have a sharp curve, so we reduce we decrease the number of this particular gamma. Okay, so that would be gamma correction and gamma encoding function. So we take a look at here. So the this image and that image would be the original and corrected. So while this one and this one is basically viewed in the same monitor. Okay, so this one is the different this is the original images. So this one is the 2.5 gamma intensity has been changed. So that would be the things. Okay, so intensity RAM B is viewed by simulator, same image with 2.5 here. Okay, so C is gamma corrected. So basically this one is if the gamma corrected from the original, while this one is corrected image from the same view, gamma corrected as on the same from this particular image, right? So we can see the shading of the black area of this particular area has been changed by itself by changing the gamma value, right? Okay, so the idea of changing the power law gamma transformation is happen in, I think, majority of that particular function is occupied in the MRI, okay, in the medical. So whereby the A1 this area cannot be seen so much about the fraction has been happened at the spine of one patient. So by using the using the gamma differently, okay, so but the C is constant for the all, but only gamma has been changed. So remember, this is the gamma. So 0.6, 0.4, 0.3. So this one is 0.6, 0.4, 0.3. So we can see that the fracture for this particular image is happen to more reliable in 0.41 compared to this one is overexposed. Okay, so I think 0.2 is not practical for the image enhancing, while this one is good enough to expose the fracture region from the spine, right? So meanwhile, reducing meaning this one, guys. Okay, so we try to limit the area of black. So this one is the blackish, this one is reduced black, this one is kind of gray, this one is light gray, right? So meaning the more that we push on the top left corner, so basically the idea of having a lighter or good enough quality for checking the fracture of the spine, right? Okay, the second, okay, just now we talk about reducing the gamma value. So now on, we try to talk about increasing the value. Okay, so increasing means this one, right? So whereby we want to push the black more than white area, guys, because the original aerial images taken from the satellite happen to be very contrast. Okay, so then by using the power law intensity, basically we can reduce the high contrast to be darker a bit in order to observe it clearly from the sky, right? So that would be the idea of setting the value of gamma to bigger and bigger based on the requirement from 3.0, 4.0 up to 5.0, right? So then the next one is a piecewise linear transformation function, the fourth one, I guess. So in this particular transformation function, we have three types: contrast stretching, intensity level slicing, and bit plane slicing. Okay, so we have three. So the first of all is contrast stretching. So contrast meaning, if we talk about contrast, a low contrast meaning we have very kind of not good in vision, okay, because low contrast, okay, so it can result a pure illumination. So this would be the negativity of low contrast, okay, because a low contrast means, as we discussed before, the range of high and low is not necessarily happen, okay, or they kind of having too many at a certain part, okay, that would be kind of low contrast images. So contrast stretching expand the range of intensity level, so whereby we want to extend this, not focusing on a certain area, guys, okay. So meaning we, as long as we have a good range of intensity from 0, let's say 255, so the more the better the image is, okay. So this one is piecewise linear transformation function, low, okay. This one is contrast stretching, so while this one is thresholding. So thresholding meaning this, okay. So stretching meaning this, okay. So we wanted to have a wide area of pixel intensity, so that we have a good visual on that particular image. Okay, so the second one is intensity level slicing. So this is quite simple. The way that the transformation function do this job. The first is we have we set a certain value, like a low pass filter kind of. So from here to here, let's say this one is 255, this one is 120, this one is 240. So in this particular intensity pixel, only available in our output image, okay. So rest will be 0, black. While the second one is brighten or darken the desired image intensity, but leave all the intensity the way they are, unchanged. So this one is unchanged, linear. So we only care about this area, like 75 to 125. So this would be particularly changed for the intensity level slicing, right? So it depends on the application. This one is one of those optic angiogram. So resulting the this one is the original one. So this one is slicing with the range intensity, okay. So the one that happened over here, and the C is resulting transformation of the selected range of near. So basically near black, okay, so that the gray in the area of blood and kidney were preserved. So whereby the preservation is happen to be in this area, okay. So that will be this one, right? Okay, last but not least, for the piecewise is bit plane slicing. So in this transformation, basically the slicing of the intensity happen where the idea of 8, 7, 6, 5, 3, 4, 3, 2, 1. Okay, this one is a bit happen when we presented this particular original image into only 8-bit, okay. So meaning this bit. So while the lesser one will be not necessarily giving us more information. So the most will be given us information is this, okay, the first 3, so 8, 7, and 6, while the others is just producing the idea of background, or this similarly happen everywhere, right? So that would be bit plane slicing. Okay, right. So the second part of this particular lecture will be histogram processing. So I think this will be the most important parts for chapter number 3. Okay, so here, in order to visualize the image with histogram, so basically there will be a simple thing to be noted. So this one is RK. This one is PRK. Okay. So whereby the RK is denote intensity of the L level. So meaning this one is 0, this one is 1, 2, 3, 4 until 255, guys. Okay. So RK, the histogram for the RK is basically the numbers N. So N the numbers of pixel. So whereby if the case that we have 64 pixel overall, 8 times 8. So basically the intensity of all the folks over here is calculated as 64 times. Okay. So whereby this could be 8, 8, 7, 6 and so on. Sum together will be 64. Okay. So to normalize them, basically we call it normalized histogram SF as the probability P RK. So P RK is the vertical axis. Happen the numbers. Example, this one is 8 for 0. So N0 is 64. So this one is N0 is 8 times by 64. So this will be the value of 0 point something. Okay, so that would be the idea of PRK. Okay, so whereby M and N is the width and length. Okay, so that would be the idea of histograms or image histogram, whereby each of the image has the histogram. Okay, this one will be the example. Okay, like I mentioned earlier about the, remember about this one? Which one was that? Hold on. We did talk about just now. Okay, maybe earlier. Okay, so this part reflecting darker, and this part reflecting whiter, and this part reflecting low contrast because it focusing on certain parts only. And the most best quality of the images is basically the RK is scattered from all the RK values from 0 to 255, let's say for the 8-bit images, right? So I think this probably happened when you have so the one that have the mirrorless camera, I think easy to see because they will be display, right? After you you press the button of the SLR or mirrorless camera, so basically there will be image right here. So they have the graph over here. So I think RGB separately, intensity and so on. So that will be beneficial for image processing. So that's the reason why we can see that the images which has the peak for the intensity at a certain area reflected to low contrast. So that there will be the photographer realized that that image taken was low contrast. So meaning they need to retake again to be as this particular intensity graph. Okay, right. So histogram based technique, we have two things: histogram equalization, and the other one is histogram matching. So I think we will focus on the histogram equalization at first. Okay, so what is the histogram equalization do is basically providing this is the image for input. This one is image for output. So because the R and S, so remember this one. So this one is referred to this. This one is referred to this. Okay. So an arbitrary PDF. PDF is basically the probability distribution function for the kind of probability idea of discussion. Okay. So result of applying the equation 3.1 to input PDF. So this one is basically when we solve the discussion of the PDF. So because if we have this, okay, I'll try to make, so initially we have this, right? So S is equal to T and R. So whereby if we try to find the R, we can also use the inverse transformation of S, right? So using T, okay? So that will be the basic idea. So this is the output. So this is the input, right? Okay, so the idea of finding the PSS over here is to have the PRR by DRDS. Okay, so that will be the idea of having this from this, the multiplication between the PDF for the input with the distribution, okay, of S of R by S, right? So one more thing is S equal TR here, right? Is basically taken from here of R, PR. Okay, this time around I use W over here. So it can be anything lah over here. Okay, because we want to prove that the 1L1 is the square of that particular things, right? Okay, so in order to find the this one, so the first thing we need to find this. So what is DRDS? So we have in hand the SDR, right? So this one, hold on, we take from here. Okay, so we do have this. So we do have this, and we do have this, right? Hold on. Okay, and we can put it out this, and we have that. We have this. We have that. So then we have this and that. So basically, the differentiation of S by R is L minus 1 PRR. Okay, so PDF or R. So then we can say this equation. Okay, so PSS PRR is basically 1 over L minus 1 PRR. So that would be PSS by this one. Okay, right. So we have this one. Okay, so by this, this one is basically for the output one. Okay, so this one is for the input. So remember, this PRR originally taken from the earlier slide. I think B and K M times N. So remember this one. So because this one is reflecting the one single line on the PRR to RK over here. So when we RK is NK is the number of RK count. So meaning, let's say we have 864. So meaning, what is the probability? So that would be a graph, right? That would be the thing. Okay. So the idea of showing the equalization happen from here to this is basically this image. So we have the original image and we have the equalization image. Okay, after we apply the histogram equalization, so we can see that maybe this particular images could be better, and maybe some person disagree about this, right? Okay, so take a look at here, equalization, guys. Okay, so the keyword, so this one is low contrast, so this one also quite low. So in order to change the paradigm to be as equalized, basically this idea will be used for, sorry, this idea will be used here in order to get here. Okay, so at the end of the day, we have a long range. Okay, see, a long range from 0 to 255, let's say. So it's very clear, right? Compared to the 4. So I think this slightly different than the 3. 1, 2, 3, right? So that would be the difference. Okay, okay, right. To do this, basically, we have some thing to be how to say, to be presenting. So let's say this one is given and this one is the S, right, guys? So this one is transformation, guys. Transformation is this. So the one that I calculate just now, where is that? Okay. This one, guys. Okay, this. Okay. So S is this one, SK. Okay. So this equation will be used over here. Okay, in order to find, because the one that we discussed earlier is 0 until R, right? Whereby we have, so this one is the continuous. So in order to make things happen in discrete, so basically we need to change this one. Let's say J, K, P, R, R, J. So meaning the K is depending on let's say 255 ke, okay, right? The value of the maximum value of the intensity. Okay, so now by having this equation from analog style, so this one is analog style. So the one that we wanted here is discrete. So discrete, whereby we use the sum. Okay, so right now we use the sum in order to find this transformation, and this one is basically the equalization histogram. All right. So how to get this is one thing. Okay. To do this, basically, I will be erasing for a while this one. I'll be showing up you one example. Hopefully, it will be beneficial to you guys in order to understand the whole concept of equalization, right? Okay. So this one is happen to have ERRK. This one is 0.9, right? So this one is 0.25. This one is 0.21. So by pulling this one, this one is 0. If we want to find this as 0, basically this one could be as R0. Okay. So whereby this one is R0, guys. So R0 is 798. 4069. Okay, the things has been used over here is for 6 pixel. Okay, so whereby, so this one is 019. So this one is basically NK MN, right? So for every each. So meanwhile, this one is one value for R0, this one is R1, this one is R2, and etc. Okay. So now, in order to find this, so this one is 8. 8 minus 1 is 7. So L is 8, 7. J0 K PR0, right? Over here. So K now is 0, so meaning PR0 only 1. So PR0 is 0.9 times 7. So 0.9 times 7 is 1.33, guys. Okay. So then we need to find S1 TR1 equal, okay, this one is multiply 0.19 plus 0.25. Okay, because of the sum, guys. So meaning K now is 1. So meaning we need to sum 2. 0.19, 0.25. So we have 0.44. Okay, times 7 is 3.08. So 0.44 times 7 meaning 3.08. So 3.08 is basically 1.3 is basically this one. 3.08 is basically this one. Okay, so that would be S. Okay, S0, S1, and S2, S3, S4, and etc. Okay, right. Until the end. Okay, in order to find the PSS, as the R0 is 798, right? So S3, S0 is 1.3. Okay, so we need to simplify them to 1 because of the probability, guys. This one is 3, right? Okay, meaning now the S0 equal 1. So R1, let's say this one is 1019. This one is 25. S1 is 3, guys. Okay. So this idea basically happen to find S0 is 1 is basically the idea of R0. So we have 798 because S0 equal 1. So meaning this one is 1, right? This particular value is taken from here. Okay. So meaning this value will be reflecting to 0.19, but the S is 1. Okay, so when S1 is 3, so S3 meaning here. Okay, so S3 means we have the value of R1, right? So R1 is 10234061 is 0.25. So basically 0.25 is the second value. So right here. So regards to the S1 is 3, so 3 is basically the value for SK. Okay. So then this one, so the 1 is basically stand for here, S0, right? So until the end, basically we can plot the 5, 1, 3, 5, 6, and 7 only for 8 bits. Okay, so the rest would be not displayed in histogram equalization. So that would be discussion on equalized histogram on here, right? So I think that would be interesting to be redo again at home. Okay, so histogram matching specification is whereby the similar as what we have just now. So we have the probability of input image. So this one is PZ is basically the PDF for the output. Okay, so this one is the expected. So while this one is the transformation, so this one is the actual. Okay, so we try to compare this and this. So that's the reason why the matching is coming in. Okay, straight away finding the output and move out the transformation and having the PDF for ZQ. So then we compare these two. Okay, so this one is comparison between histogram equalization and histogram specification. We have several images to be discussed. So this one is image, the original image with the histogram. So HE transforming using the histogram B. So basically the equalization using this one happen here. So this one is the histogram equalized image. We transport the image as S. Okay, and this one is the equalized image from histogram for the equalized image. Okay, so we can see that the area of this particular things can be seen right now. Okay, so similar goes to this one too. We have this one for the idea of transforming the G, Z, Q, and so on. Okay. Right. So next one is the local histogram equalization. So we have original result. This one is original one. So result for the global. So in the local histogram equalization, there will be two, global and local, guys. So the global happened, the one that we done just now. Okay, this one is locally. Okay, histogram equalization. So here, see, basically, if we try to look it in very closely, so we can easily see one thing is happening inside the black box. So the idea is when this particular image are too close to intensity of the dark square, so basically a human face the difficulties for seeing things. Okay, so whereby if we try to see this unseen, we need to localize them, because if we try to make things globally like the one that we have here, okay, from here to here, so we will face this kind of result, guys. Okay, so it's not beneficial images for us. Okay, likewise, if we try to look it up to the local histogram, so we can see that this one, the 5 images could be clearly significant in the way that the image is differently exposed to us. Okay, so the idea is the second idea for the local histogram statistic is like this, by using the statistical approach. Okay, so whereby means and variance is utilized with the flexibility of the parameter. So then this one is one of the powerful technique to enhance the unseen things to be seen things, right? So I think that's all for this particular part number 1, chapter number 3. So I'll meet you on the next video. Thank you and bye. Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.